the wave in region 2 must be of this form. And then H and E1 of K2R. I have to use the Hankel function with wave number K2 because I'm solving those Bessel's equations in region 2 now. And then times an unknown, and we'll just call the unknown T12.A. This can be thought of as a new unknown, so I just call this unknown T12.A. And then I can write down the H2S in region 2, very similar to this. And then H and H1 K2R times T12.A. Okay. Then I can match boundary condition. And I can match this to that and this to that. They must be equal to each other. And then I will make use of this orthogonality relationship. I can actually pick them to be of different ends. Okay, they have to be the same m, very obvious from this expression over here, because these are orthogonal. I can pick them to be of different ends, but because of this orthogonality relationship, it will force these ends to be the same. Okay, different ends will cancel, will be orthogonal to each other. Okay. So finally, you equate this to that, and this to that. You have two equations and two unknowns. You get rid of this thing, the orthogonality. You have this equals that, and that equals that at rho equals A. Yeah, maybe this is the radius. Okay. R equals A. You make boundary condition over there. Set R equals A. And then get two equations and two unknowns. And then you can solve for your R12 and T12. So I wouldn't write them down because they're too laborious to write that. No, two vector equations, two unknowns. Actually, it should be two matrix equations. R12, T12. And then you can solve for them. You want me to write down the detail, or is that line alone sufficient to convince you that? Okay, I repeat. You match this to that, you match this to that, and R equals A. Okay? R equals A to match boundary conditions. This must be equal to that must be equal to that. Get rid of this one by orthogonality. And then I will have this equal to that equal to that. But A is arbitrary. I haven't stipulated what A should be. And I can cancel my A. Okay? So I have a matrix equation, this at R equals A equals this at R equals A, because I can cancel the A. A is arbitrary vector. Similarly, I will have another matrix equation equal to this matrix equation and cancel out the A because they are arbitrary. And I have two matrix equations and two unknowns. And just go through the algebra to find R12 and T12. Yes?
So back when you define the A and B vectors, is the B radially outward and A is tangential to the surface, or
A and B are just
arbitrary?
2 by 1 vector, right?
What's the meaning of A?
Because I have to match up on the left hand side. Remember, I erased the left hand side is pi E, pi M.
Okay.
Equals to this. Okay, A is just a 2 by 1 column vector because I have two scalar potentials that are different, independent from each other. So this is a vector A, this is a vector B to denote that. Okay, to distinguish the fact that the upper element will be pi E, lower element will be pi M. Okay. This line is enough, right? I don't want to write down anymore because they're very difficult to write. This line is good enough. Right? It's good enough. I think this is good enough. Two matrix equations, two unknowns. Solve them, you can. I'm sure you can do that. No problem. So there's another very important thing. These are diagonal matrices. This is diagonal, this is off diagonal. So when you look at this equation, these are all diagonal, off diagonal matrices. Okay? Diagonal, off diagonal, diagonal, off diagonal matrices. And when you solve for them, you find that R12 and T12 are also diagonal. What is the physical meaning that R12 and T12 are diagonal? What does that mean physically if R12 and T12 are diagonal? That's right, very good. TE and TM fields are uncoupled at the boundary. And they are uncoupled because even though you assume them to be coupled to begin with, I make no assumption that they're decoupled, went through the mathematics, went through the boundary condition mapping, tangential E, tangential H, been continuous. Finally, when I get the matrix equations, I find that R12 and T12 are diagonal. Upper component of the column vector A means pi sub E, right? Pi sub E is a TM wave. And then lower component means the TE wave, which means that the TE and TM waves are uncoupled in this spherical layer medium. That at least for one interface, they are not coupled. And if you put in more interfaces, they will still not be coupled. Is this clear or is this not clear? Maybe it takes a little bit to sink in. You have to meditate. And it will sink in, right? So the thing about, in my experience, things in one dimension is very simple. Things in three dimensions is very simple. Things in two dimensions is always harder. If you want to do analytic mathematics. This is an example of a 3D problem. This is truly a 3D problem, right? A sphere sitting in a 3D space. You find that TE and TM waves are decoupled. But if we go to 2D, TE and TM waves are coupled, making things very messy. Similarly, if you look at spherical Bessel functions, spherical Hankel functions, they're actually very simple. You know what they are, the zeroth order, like H0, 1, AR. You know what it is? It's very simple. I think it's something just like that. Something like that, okay, very simple. But what is this in a cylindrical coordinate system? Very complicated, right? You have to have a power series, you have to do things by Frobenius method, you have the singularities, very, very complicated. You have a branch point singularity at the origin, if it's this one. Okay, and then this one is also very simple, J0KR. I think it's just that one over that one. But then, right in cylindrical coordinate system, it becomes very complicated. My experience in life is that things in 1D and 3D are very simple. Things in 2D are very complicated. Why? I don't know why. I think 2D is not real. We never had anything that's really 2D, right? 2D, right?
Graphene, like layers.
Graphene?
Yeah.
Well, if you assume graphene to be infinitely expanded, then it's true. But there's no real 2D problems in this world. That's why 2D problems are very complicated once it comes to mathematics, like Hankel functions, and even boundary conditions, and they will give you TE, TM coupling, okay? So you get this reflection coefficient, and they're all derived in the textbook. I wouldn't want to write them down again. But I want to teach you one more thing before the bell rings. Those reflection and transmission coefficient can be simplified by using what is called a Wronskian. Does anybody know what a Wronskian is? Some of you have heard of it. I see some heads nodding, so you know what the Wronskian is. It turns out that when you look at those reflection coefficient and transmission coefficient, they look very complicated, but some parts can be simplified using the Wronskian. What is the Wronskian? Okay, let me write the Bessel equation down for Bessel function. Well, let me just do it for cylindrical coordinate system. Okay, you can also do it for spherical coordinate system or cylindrical coordinate system. The Bessel equation is something like this. Right, this is in cylindrical coordinate system. Say I find a second solution to this Bessel equation. With the same n, but different functions. Okay, maybe I call it a and k rho. So this could be Bessel-Neumann function, Bessel-Henkel function kind of thing. But this must be true for both of them.
Okay. Repeat K row, K stub row.
What?
K stub row instead of K row.
Oh, you can put k sub rho here, but let me just save some writing by just writing k. Okay, let's assume kc is equal to 0. So k is always k rho. Okay, so to do this very quickly, you multiply this by an, bn. You subtract the two equations. This actually discovered by Mr. Wronskian, must be many, many years ago. But if you look at this derivation, it's very similar to Green's theorem, how you derive Green's theorem. So you multiply the two, and then these terms will cancel each other. So you have an over rho, partial rho. Or multiply by rho also, okay? So that this rho goes away. Partial rho, partial rho, bn minus bn partial rho, partial rho. And must be equal to 0. Very much like how you would do Green's theorem. Okay? And then similar to the tricks of Green's theorem, you try to write this as a total derivative. This must be the same as partial rho. Partial rho. an rho, partial rho, bn minus bn rho, partial rho, an. I think this is correct. If you take this derivative, you get above, right? You take the derivative of that thing, you get above. Am I right? Let me think. Yeah, you get that. Okay? This must be true. You take the derivative using a chain rule, you get this term plus second term. You take the derivative using the chain rule, you get this thing plus the second term. The second term always cancels, like the derivation of Green's theorem. There's always a middle term that cancels. This means that if this is equal to 0, this must be a constant. An rho, partial rho, bn minus bn rho, partial rho. And this is constant. So the derivative of Bessel function multiplied by another solution to the Bessel's equation minus that solution multiplied by its derivative always equals a constant. So this is a simplification you can use to simplify the reflection and transmission coefficient. It's called a Wronskian. But I don't know what period it was discovered. Maybe it's discovered in the 1600s or even before Green's theorem. But later on, if you look at the derivation, it's very similar to Green's theorem. George Green lived around 1800s. And Wronskian, I don't know, maybe 1600s. Okay, because these ODEs came about very many years ago. Bessel's equation and other things came about very long time ago. Maybe 1700s, I don't know. But it was called the Wronskian again. But you can gain the insight to how it is derived from the Green's theorem method. Okay. I think it's not time. And we convene again next Tuesday at 9 a.m.